Lab 3 magnetic field of a bar magnet. So the purpose of this lab was to measure the distance dependence of the magnetic field due to a small bar magnet and compare our measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived by the Biot-Savart law, and calculate the experimental value of a bar magnet's magnetic dipole moment and write the code to visualize that magnetic field. So here are some important concepts that we use. So the magnetic field of a bar magnet, the Biot-Savart law, as shown here, the distance dependence of the magnetic field of the bar magnet, superposition principle, linearization, and here are our main results. On the on-axis component for the procedure of this, we downloaded a magnetometer and located the chip on the phone that measures it, and we lined it up with direction of north, where B, the x position of B, was equal to 0, and we measured the distance between the chip and the bar magnet. Initial conditions were that the phone was lined up in the direction of north and that the magnet was aligned with the magnetometer. For the off-axis component, we needed to find D perp, where the magnitude of B net is equal to 100 micro T. Measure the value of the Y component of the magnetic field of the Earth. Find D, as shown in the bottom image, and find the vector components, which is the X, Y, and Z components of the net magnetic field at this location, and then correct it for the Earth's magnetic field. Some other information, like assumptions that we made, were that the bar magnet can be treated as a magnetic dipole. Only the magnetic fields present are from the Earth and the bar magnet. The system was the bar magnet, and the surroundings was everything else that wasn't the bar magnet. So observations: when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. We found this was true. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases. That was false. For the position of the magnetometer has no effect on the measured x component of the magnetic field. We found this was false. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. We also found this to be true. So here's the data that we did find, and here is the graph for the linearization of our data. And here was how we calculated N and our mu for the magnet. And these were two results. So N and here's the code that we used for the actually plotting out and illustrating this concept. And here's the rest of the code. And here is the computation model, where the orange, the magnetic field on the axis, the cyan is the magnetic field perpendicular to the axis, and the magenta is the magnetic field at 45 degrees from the axis. So some error was that we found that the computational model found that our values were for 15.9206 T versus experimental was like 12.612 T. So for our value of R in the calculation of the magnetic dipole moment, the average value of the magnetic field was used to find R in mu of the magnet, and the experimental value of D was used for R in the computational model. That could have been a source of error. Magnetic fields that were not accounted for in our calculations could have made some error. An inconsistent angle of the phone when measuring could have also caused some error, and inaccurate readings from the magnetometer. For the what if you hadn't oriented your experiment to compensate for the magnetic north and had instead laid out your meter stick at some intermediate angle with respect to the Earth's magnetic field? How would your results have changed? Our values would have been very different, but we could find and isolate the magnetic field of the magnet if we knew the angle between the meter stick and the magnetic north of the Earth. However, it would be much too complicated for us to calculate at our current level of understanding. What if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? The direction of the combined magnetic fields would be the same. However, the strength of the magnetic field would be stronger than if it was only one. And that's it. Thank you.